Okay, good afternoon, everyone. Or I guess it's not afternoon for you necessarily, but it is for me. So I actually just spent about an hour recording the solution video for this practice exam, only to find out that I had my microphone muted for the whole time. So I'm gonna do it all over again because I'm a dum-dum, I guess. Um, but okay, so on this page, I was talking about, I just wanted to give you an idea of what is going on with this practice exam. So there's basically 6 questions, and the practice exam is not necessarily a carbon copy of the actual exam. Okay, I picked some random topics from the selection of things which we have covered so far, and that's what I'm going to do for the exam as well. But they might not be the exact same things which you see on this practice exam, but this practice exam should give you a good idea of whether you understand some of the core concepts and give you an idea of what kind of questions I asked on exams, what is the exam going to look like, what is the format going to be, those sorts of things. So definitely don't take it as like the end-all be-all of your studying. You should also practice the homework questions, take a look at the extra problems from the notes, take a look back at your notes, make sure that you have all the log rules memorized, know how to graph all of the major functions, do graph transformations, and all that stuff. So yeah, I guess I'll just remind you about when the exam is. The exam's going to be on February 17th, so that's this coming Thursday in class, and we're going to have a review day on February 15th, so the Tuesday, which is coming. So it would be really helpful for the discussion if you came with questions. So take a look at the problems in the back of the book, take a look at the problems in your homework, take a look at the extra problems from the notes and from this practice exam, and find out which ones that you're confused about and come to class and ask about them. I'm also going to have office hours that day from 3 o'clock to 4:30 in Microsoft Teams, and they're going to be SI sessions on Monday and Wednesday. So, I think the Monday one is going to be as usual, and the Wednesday one is maybe going to be double time or something like that. So those ones are in closed hip. I don't remember the room number, but it's on Blackboard. So to study for the exam, I'd recommend try the practice exam under exam conditions. Okay, try all these problems on your own before you watch this video solution guide. And I think that will help you to gauge whether you have a good understanding of some of the class concepts or whether it's not as strong as you thought it was. Yeah, so I guess I'll start then. So for this first problem, okay, okay, how am I going to do this? So I already solved this entire thing. So what I'm going to do is actually I'm just going to post this solution to Blackboard. And in this video, I'm going to go through my thought process for how I solved all of these problems. And I'm just going to use the green highlighter to show you what I was doing on these problems. So for this problem, we have the linear function f of x equals negative 2x plus 8, and it's modeling the weight in ounces of chips left in the bag on the xth day. Okay, so we're supposed to draw a graph of this function below. Okay, so the way I drew this graph was they gave us the function already in slope-intercept form. Okay, so if they give it to us in slope-intercept form, okay, then it's pretty easy to graph because I already have the y-intercept or the vertical intercept, right? It tells us, well, if I plug in 0 into the function, then I get negative 2 times 0 plus 8, which is just 8, okay, which tells us that the point 0, comma 8 is going to be on the function. So that's how we make a graph. We just take x values, which can be seen here on the horizontal axis, and the way we get the height of the function is by plugging those x values in for x in the function. Okay, so the very first one I graphed was this point here. This is the y-intercept. And from there, what I wanted to do was just think about, well, what is the pitch or the slope of the function going to be? Is it going to be going up, going down? What's happening here? Well, we are told that the slope is -2. So if we write -2 as a fraction, what it's telling us is, well, the rise is -2 and the run is 1. Okay, so for every 1 box that I move to the right, I'm going to move 2 boxes down. So that's how I went, okay, down 2 over 1. Down 2 over 1. This is how I graph a linear function. Okay, and then I just connected all of those dots with a line. Okay, so pretty simple stuff. And the next part of the problem was to find and interpret the horizontal and vertical intercepts. Now the horizontal intercept is going to be when the function passes through the horizontal axis. The horizontal axis is the one that goes left and right, okay? And the vertical axis is the one that goes up and down. So the intercepts are where we intercept that axis. So the horizontal intercept can be seen here in blue, and the vertical intercept can be seen up here. It's just the one that's given actually by the problem, right? It's their b value. So the way I'd write them down is as follows. I'd write 4, 0 for the horizontal intercept, and I'd write 0, 8 for the vertical intercept, okay? Because if I count 1, 2, 3, 4, it's 4 over and 0 up and down, right? So that's 4, 0, and then the other one's 0 over left and right, and 8 up. Okay, so now we're supposed to interpret them. Well, what I want to think about is, what do x and y mean in the problem? Well, the x value is the day that we're on, and the y value is the weight of chips left in the bag. So if I interpret the first one, it's telling me that on the 4th day, there are 0 ounces of chips left in the bag. Okay, so I wrote that down. On the 4th day, excuse me, all chips are gone. Presumably they were eaten. Okay, and the other one is, well, the x value is 0, so it's the 0th day. So on the first day, I guess. And there were 8 ounces of chips left in the bag. Okay, so that's how we interpret. We just think about, what do these numbers represent in terms of x and y, and what do x and y represent in terms of the problem? All right, the next question was to find and interpret the slope. So we actually already did that. To graph this thing, we found that the slope was -2, so m is equal to -2, and the way I think about the slope in terms of the problem is, this is the rate at which my substance is changing, okay? So it should be expressed as a rate, okay? So in this case, it's -2, so for each 1 day that I move over to the right, the number of ounces of chips in the bag goes down by 2, which tells us that we are eating 2 ounces of chips per day. Okay, and the last part of this problem was to ask ourselves, okay, is f prime of 1 positive? Why or why not? Well, we need to remember first that f prime of 1 is simply the instantaneous rate of change of our function at x equals 1. Okay, so it would be if we went to x equals 1 and we drew a tangent line, but of course a tangent line to a line is just that line itself, because linear functions have a constant rate of change. Okay, so the rate of change of a linear function is just the slope of that function. So I would say no, f prime of 1 is not larger than 0, because f prime of 1 is -2. Right? We have a decreasing function here. It's going down, so the rate of change is negative everywhere. So if f prime of 1 is the instantaneous rate of change at x equals 1, it can't be positive because the function's going down the whole time. Okay, so next question was question 2. I usually do a true and false at some point in the exam, so usually I'll do this like A through E. true and false questions. And what I'd like students to do is, okay, if it's true, you can just circle true. If it's false, I want you to circle false and briefly explain why it's false, okay? So just give a brief explanation. So this first question, we have an exponential function has a constant rate of change. As I just discussed, if a function has a constant rate of change, it's going to be a linear function. So I could say, false, constant rate of change implies linearity. I could say something like that. Or I could view it in a couple different ways, right? I could also view it from the graph. Well, I know an exponential function looks like this pink line here. And I can see that the rate of change at this point is equal to the slope of this tangent line, and the rate of change at this point is equal to the slope of this tangent line, and I can see that these slopes are clearly different from one another. So that would be a graphical argument for why an exponential function has a non-constant rate of change. Or you could also take a look at the average rate of change of the function y equals e to the x on the interval from 0 to 1 and then on the interval from 1 to 2. If you do it on 0 to 1, you get e to the 1 minus e to the 0. So that's just e minus 1 and divide by 1. So you get e minus 1 as the average rate of change on this interval. But then you do the average rate of change on another interval and you get e to the 2 minus e. Okay, so e is a number. If you square it, subtract it from itself, it's not going to be the same as doing just e minus 1. Okay, so these numbers are not the same. You can check it on your calculator if you want. So the average rate of change of the function on two different intervals was different. So that's an analytic way of solving the problem. Okay, so the next problem is interest compounded continuously always has the same result as interest compounded annually as long as k is equal to r. Well, we have seen a million times in class that that's just not true. Continuous interest rate is not equivalent to an annual interest rate. That's why we have those problems which ask us to do it both ways and explain which one is better, right? So the bank is always going to try to pull a fast one on us and give us a funny interest rate that makes us confused to try to pull a fast one on us. But you can also see this algebraically. So what I was doing here was I just said, okay, p naught e to the kt, set it equal to p naught times 1 plus r to the t. Okay, and then all I did was I canceled the p naughts and I took the tth root. And I get the equation that e to the k is equal to 1 plus r. Okay, which tells us that r is equal to e to the k minus 1. Okay, and that's not the same thing as k, right? E to the k is not equal to 1 plus k, right? If r and k were equal, then these two things would be equal, and I could replace r by k. And e to the k is not equal to 1 plus k. It's definitely equal to something else. All right. So the next question is a tricky one. It's a log rule, but actually it's the reverse of a log rule. The log rule we learned in class was that the log of two things getting multiplied is equal to the sum of those two logs. And the rule which we're given in the problem says that the log of a sum is equal to the product of the logs. Okay? So this is backwards from how it should be. It's the log of a product is equal to the sum of the logs. So you could just say no, the correct rule is like this if you wanted, or you could say, you could also view it in another way. You can just check if it's true for a given set of x and y. So I picked x equals 1 and y equals e, and I checked. Well, if you do ln of x plus y, that's just ln of 1 plus e. And I should check, is ln of 1 plus e equal to ln of 1 times ln of e? Well, ln of 1 is 0 and ln of e is 1. So that would mean that ln of 1 plus e is equal to 0. But I know that's not true because I know the natural log function is only 0 when the input is exactly 1. So this is a contradiction, right? So that would mean that 1 is equal to 1 plus e, but that would mean that E is equal to 0, which is not true. So that's another way I could solve that one. So, basically, the whole point of this is to say, well, if you have a rule and you want to say it's true, then I can say that the rule is not true as long as I can find one example where it's false. Because the rule says that this is true for every x and y. So if I can find an x and a y such that the rule isn't true, then it's not a rule. All right, so next up, okay, the next one was e to the ln of x plus y is equal to x plus y. So if you remember one of the rules, you can just immediately verify that this is true, okay, because e and ln are going to cancel one another out. But the other way you can see it is if you were to take the natural log on both sides. Then you would get ln of x plus y on the right-hand side, and you would be able to bring this power down front on the left-hand side. So you would get ln of x plus y, that was the power, times ln of e. And you know that ln of e is 1. So then you get the equation ln of x plus y is equal to ln of x plus y, and that's true. So what we verified here was that this statement is equivalent to a statement which is categorically true. It's very obvious, right? This same thing on the left-hand side as the right-hand side. This is true. Okay, so that's how you can see that. And the last one says, the average rate of change of f of x on an interval from a to b is equal to the slope of the tangent line to f of x at x equals a. And this is going to be false because the slope of the tangent line, remember, is what we called the instantaneous rate of change. And the instantaneous rate of change is not going to be the same as the average rate of change unless you have a linear function. Okay, so a graphical way of seeing that is the average rate of change, right, is the slope of the line which passes through a comma f of a and b comma f of b, right? So it's the slope of this red line, whereas the slope of the tangent line can be seen in green here, okay? This tangent line comes in, just barely kisses our function at one point and moves on in the same direction, and we can see that the slope of the green line is not the same as the slope of the red line. So this is an example of when the average rate of change of f of x on the interval from a to b is not the same as the slope of the tangent line at a. All right. So question 3 is a super standard, frankly, fairly straightforward profit, revenue, cost function problem. Okay, so George has a banana stand which costs him $5,000 to purchase, so that's his one-time payment of $5,000, and then he buys bananas at the grocery store for 25 cents each and freezes them and sells them for $1. So if we want to find the equation for George's costs, we just have the one-time payment $5,000. The reason I don't put a Q here is because he's not paying $5,000 for every banana. He's just paying $5,000 once to get the stand, and then he's paying 25 cents per banana thereafter. So that's the cost function. And the revenue function is, of course, just the money that we get from selling bananas. Okay, so for a number of bananas that we sell, how much money do we get from the customer? Well, it's just $1 per banana, so it's just Q. 1 times Q is Q. To find the profits, of course, all we have to do is take our revenue and subtract the costs. So the one thing to be careful about here is when we subtract this cost function, we got to use these parentheses here to make sure that we subtract all of the costs. So you got to do the minus 5,000 and minus 0.25Q. So you actually get 0.75Q minus 5,000 as our profit function. So if we want to know how many frozen bananas George should sell to break even, then we just need to say, well, we need to take the profit function and set it equal to 0. That means we have 0 profit, means we break even. Or we take our revenue and we set it equal to our costs, whichever way you want to do it. I did it with the pi of q equals 0 here, and I got 6,666.6 repeating. Okay, so the way I decided on 6,667 was not simply by rounding this function, or this number, but actually by thinking, well, if I sell 6,666, then I still have a small loss. And if I want to talk about how many bananas I need to sell to break even, okay, it should be the first one for which I pass zero profit. Okay, so that would be 6,667, because after that, I'm going to start earning money. Okay, and then the marginal profit, well, remember the marginal profit is just the rate of change of the profit function, which in this case, the profit function is linear. This is the form mx plus b, right? Or mq plus b. So in this case, the rate of change is just the slope. So with units, that means dollars per banana, right? $0.75 per banana. Okay, so the next question is a little bit tricky. Okay, so this problem starts off and makes us think, well, maybe what we need to do here, okay, let me just read it. So in 2012, there were 6 hamsters in my basement. In 2015, the hamster population had doubled. So it starts off kind of like a doubling time problem. And then it says h of t measures the number of hamsters in my basement, where t is in years since 2012. What is the average rate of change in hamsters from 2012 to 2015? And the one thing that they kind of leave out is they don't tell us whether the relationship is linear or exponential or something like that. So I might start this problem by trying to write down, well, what is h of t? Is h of t equal to h naught times e to the kt, or is it equal to m times t plus b? We don't know. But that's kind of irrelevant for the purposes of the problem, because we're asked, what is the average rate of change in hamsters from 2012 to 2015? Which I know the average rate of change is nothing but h of b minus h of a over b minus a. Okay, that's how I get the average rate of change. So all I really need to know is how many hamsters I had in 2015, how many hamsters I had in 2012, and then subtract those two numbers for the bottom. So really I want to know what is the average rate of change of h of t on the interval from 0 to 3, because t is in years since 2012. So if it's 2012, it's been 0 years since 2012, and if it's 2015, then it's been 3 years since 2012. So I find h of 3 minus h of 0 divided by 3 minus 0. Now the only other tricky thing here is to think, well, how many hamsters do I have in 2015? Well, if I started with 6 and in 2015 I had double that, then that means I had 12 hamsters in 2015. So I get 12 minus 6 over 3, which is 2 hamsters per year. So, bit of a sort of conceptual question here where we didn't really need to do too much, to be honest. It's just interpreting what is this question really asking. All right, so the next part says, okay, actually it is an exponential function. So we're supposed to calculate the average rate of change of h of t over smaller and smaller intervals in order to estimate the instantaneous rate of change. Okay, so what I did was I did the average rate of change on the interval from 3 to 4, and then I did it on the interval from 3 to 3.1, and then 3 to 3.01, and then I finally did 3 to 3.001. Okay, so the way you do that is just by doing h of 4 minus h of 3 over 4 minus 3, right? So I just plugged in 4 for t in this equation, and I plugged in 3 for t to get this second number. Subtract those two, divide by 4 minus 3, and I got 3.12. Okay, so what I'm after here is h prime of 3. So this is the average rate of change of h over the interval from 3 to 4. So then I do it from 3 to 3.1, and I got 2.8. I did it from 3 to 3.01, and I got 2.777. And then I did 3 to 3.001, and I got 2.77418. So at this point, I can see, well, it looks like the first 3 digits of this are pretty much fixed at this point. So, or not first 3, but the first 2 decimals, right? So I would say all we're supposed to do here is estimate. I would say 2.77 is good enough of an estimation for this problem. So I would say that h prime of 3 is approximately 2.77 hamsters per year. Okay, so the way we visualize what's really happening here is what we want to know is the slope of this pink line, okay? So what I do is first I check, well, what's the slope of this red line? And then I check, what is the slope of this blue line, right? Where I take it over a smaller interval. So the red line passes through these 2 points, and then the blue line passes through these 2 points, right? And then I just keep moving this point here down until it's almost on top of the point where I want it. And the slopes of these lines get closer and closer and closer to the actual slope of this tangent line, which is what I want to know. So I say, well, I did this process and my numbers were getting steadily closer to something like 2.77. So I'm going to guess that the actual slope of the pink line is 2.77. All right. So next up, we have question number 5. So we have a bank which is offering an investment which earns K% interest compounded continuously. So they don't tell us what is the percent interest. And we invest an unknown amount of money. So they also don't tell us what is P0. What they do tell us is that in 1 year I have $500 and in 2 years I have $700. And we're supposed to find a formula for P of T, which is the amount of money I have T years after my initial investment. Okay, so the very first thing that I would do solving this type of problem is write down the general form of the equation I'm after, which in this case, since I'm using continuous interest, I use the continuous interest formula, which is P of T equals P0 times e to the kt. Okay, so what I need to do in order to solve this problem is to figure out what is P0 and what is k. Okay, so here's how I do that. The first thing I do is I write down what is the information that's told to me by the problem, and that is in 1 year I have $500. So that means that P of 1 is equal to 500, and the way I get 500 is by plugging in the number 1 for T in the equation P0 e to the kt. So I know $500 is equal to P0 times e to the k, and I know that $700 is equal to P0 times e to the 2k. Okay, so what do I do with that information? Well, I want to know what k and P0 are, so I have 2 equations and 2 unknowns. I need to eliminate one of the variables, and I see that I can easily do that by taking these 2 equations and dividing them by one another. So what do? I'm going up here. I take 700 and I divide it by 500. Now I know that 700 is equal to P0 times e to the 2k. So I replace 700 by P0 e to the 2k. And I know that 500 is equal to P0 e to the k. So I replace the denominator, 500, by P0 e to the k. And when I do this, I see that I can cancel the P0s. And I'm left with just e to the 2k divided by e to the k, which we should recall that the way we simplify something like this, if we have a number to a power divided by that same number to another power, the way we combine these is by subtracting the powers. So I get e to the 2k minus k. Well, if I had 2k and I take away k, I'm just left with k. So I get e to the k is equal to 700 divided by 500, which is 1.4. So if I take the natural log on both sides, I can find out that the k is just this crazy decimal, right? This is what I get when I do the natural log of 1.4 on my calculator. So ln of e to the k is just k. All right, so that was how I figured out what k was. So at this point, I've got k. So I have the equation P of t is equal to P0 e to the 0.336472237t. And now I have to find out what is P0. And that's the tricky thing, is they actually don't tell us what is the amount of money, right? They tell us that after a year I have $500, so presumably I started with less than that, right? So all I'm going to do is, now that I have k, I'm going to substitute it back into one of these two equations. I chose this one because if I do it this way, I don't have to multiply k by 2, I guess. So I got 500 equals p naught times e to the 0.3364722237. And I actually remembered, by the way, that that this is just e to the k, which, if I remember from earlier, I know that e to the k is 1.4. So this just saved me a little bit of time not having to type as much stuff on my calculator. I just said, well, this number is just 1.4, so all I have to do to get p naught by itself is to divide 500 by 1.4, and that gets you something like 357.14. Okay, so for this situation, we finally have p naught and we have k, so p of t is equal to 357.14 times e to the 0.3364722237t, which is also just equal to 357.14 times e to the ln of 1.4 times t. If you want to leave it like this, that's also fine. You don't have to write out all those decimals, as long as you remember that ln of 1.4 is just this number. Okay, so the next part of the question is asking us how many years it's going to take for the investment to be worth more than $2,500. Okay, so what we want to know is, we want to find the value t such that when I plug t into the p function, I get a number which is bigger than 2,500. Okay, that's what I want to know. Well, I know my investment's generally going up, so I know that this is going to be true for any t which is bigger than the t which solves the equation such that it's equal to 2,500, right? So in this case, I just take p of t equals 357.14 times e to the ln 1.4 times t, and I set it equal to 2,500, and I want to find out what is t. So some students, I've noticed, have been making a slight error at this stage by saying, well, I know I want to find out t, and t is in the exponent, so let's just apply natural log. But this is not quite the right way of going about this, because if you want to bring this down front, in front of the log, using the power rule, then the power needs to apply to the entire thing. But in this case, it's only being applied to the e, okay? So I need to sort of get this part by itself first before I do that natural log. So I do that by just dividing both sides by 357.14. Okay, so then what am I left with? Then I'm left with, forget about this ln for a moment, I'm left with e to the ln of 1.4t is equal to 2,500 over 357.14, which is just about 7. Okay, so to get t by itself, now that I've isolated this e to the power, I just apply the natural logarithm, okay? And ln and e are going to cancel each other out here, so I get ln of 1.4 times t on the left-hand side, and on the right-hand side I have ln of 7. So to get t by itself, I just have a number times t is equal to another number. I just divide by ln of 1.4. Okay, and if you punch this in on your calculator, you get something like 5.78329. Okay, so the question is, how many years will it take for my investment to surpass $2,500 in value? Well, it's going to take 5.78329 years. Okay, and the reason that I use 5.78329 here is because the interest is being compounded continuously, which means like every second of every day, the interest is being compounded. Okay, whereas annual interest is typically only compounded at the end of the year. Okay, so if I was using annual interest, I would probably round this up to 6. Okay, I would probably round this up to 6 for annual interest. But since I'm using continuous interest, I'm actually going to have that amount after this many years, or this amount of time, right? So, bit of hair splitting here, but I would accept 5.78, or I'd also accept 6 years. That would be fine. Okay, final question. Okay, so the next question is, we want to find two non-trivial functions, f and g, such that h of x is equal to f of g of x is equal to 3e to the x plus 2. Okay, so in this case, non-trivial means that my two functions are not just x. Okay, why do I want them to not be x? Well, if you choose f of x equals x, then you can just say, well, g of x is just the function 3e to the x plus 2. And then, yeah, you plug in 3e to the x for x, or 3e to the x plus 2 for x in f, and you get this equation. But this is sort of trivial in the sense that, well, you just made one of the functions do nothing, and then the other function does all the work. So I want you to come up with two functions such that one of them does some amount of the work and the other one does the rest of the amount of work. So there's a million ways you could do this. The first way I did it was just by saying, okay, well, if g is just x plus 2 and f is 3e to the x, then if we do f of g of x, it's like doing f of x plus 2. And when I plug in x plus 2 for x in 3e to the x, I get 3e to the x plus 2, which is the function that we want. So this is sort of the opposite of how most of these composition problems have gone for you in the past. Usually they tell you f is this, g is this, find out what is f of g of x. But this is a bit of a different problem. They say, okay, f of g of x is, we give you the answer. Now you tell us what are the functions such that when I plug them in together, I get the answer. So it's sort of a reverse style question. And this is going to be like really crucially important when we learn about chain rule and U substitution for integration later on in this class. So that's why we do a lot of these types of problems early on. Okay, but you don't have to do it this way. You might say, Tom, I did it in this other way where I use different functions than you, but I got the same answer. Is it okay? And the answer is yes, sure. There's a million ways you could do this. I could have also said this other one, right? You could also say f is 3x, and g is the function e to the x plus 2, right? Then when you do f of g of x, then what you're doing is you're plugging in the function e to the x plus 2 for x in the function f. So you get 3 times e to the x plus 2. So that's also fine. You can do it that way. Or like a million other ways. All right. And the very last problem was to give an example of a quadratic polynomial q of x and solve that equation for q of x equals 0 to find the x values that cause your quadratic to be 0. So first, I want to quickly review what quadratics are, what polynomials are, and what power functions are. So quadratics are just functions that have the form ax squared plus bx plus c, where a, b, and c are numbers, and specifically a is not 0. Okay, so the number here, a, should not be 0, because otherwise this would be a linear function. So we want this term to be non-zero, so we say a shouldn't be 0. So that's a quadratic function. And a quadratic function is also a special type of a polynomial. Okay, so polynomials are functions where we take, okay, a number times x to the n plus another number times x to the n minus 1 plus another number times x to the n minus 2 plus a number times x plus a number. And all of these numbers are just real numbers, and the powers of x here are all whole numbers. So think of functions like 17x to the 9 plus 5x to the 8 plus 3x to the 7 minus 2x squared plus 3.7x plus 4. Like these types of functions are polynomials, okay? So n should be an integer which is larger than 0. So an integer means whole number, and n larger than 0 means the number should be larger than 0. Okay, and lastly, we have power functions, which are a bit different. For this function, we just take a number times x to a number, and we allow the power to just be any old real number. So we don't specify that it should be an integer. We just say it could be a real number, and it could be negative, it could be a fraction, it could be a decimal, it could be pi, it could be anything, as long as it's a real number that's not 0. So that's a power function. All right. So back to our example, you can come up with any quadratic you want. So I came up with 3 and solved them in a couple different ways. So the first one I said, well, let's use x squared plus 2x plus 1, pretty basic polynomial. And I solved this one by factoring. So what I want to do when I factor is come up with two numbers such that when I add them together, I get the middle term, 2. And if I multiply them together, then I should get the last number, which in this case is 1. So I'm looking for two numbers. When I add them together, I get 2. When I multiply them together, I get 1. And those numbers are 1 and 1. So I factor like this. And then I have this equation in the form, well, I have one number times another number is equal to 0. If you multiply two numbers together and you get 0, then one of those numbers had to have been 0. Right? So that's how we set x plus 1 equals 0. And we move the 1 over to the other side, and we get x equals negative 1. And in fact, we get the same exact thing when we solve this one, where we would subtract 1 to the other side, and we get x equals negative 1. So in this case, we have what's called a double root. Okay, then I did another one. I just came up with a really crazy one. X squared plus 31x minus 17 is equal to 0. And this one I said I'm going to solve it using the quadratic formula. So the quadratic formula is just x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, b is 31, c is negative 17, and a is just 1. So I get negative b, that's negative 31, plus or minus the square root of 31 squared. Now this was a minus 4ac, but since the 17 is negative, it's a double negative, so I get minus a negative, that means plus. So I get plus 4 times 1 times 17, right, because a is 1, so 4 times 1 times 17. And then 2a in the bottom, it's just 2. So that's using the quadratic formula. And finally, I was like, well, actually, if you wanted to be super duper cheeky, you could say, well, actually, for a quadratic, we just say that we take three numbers a, b, and c, and a should not be 0. But I don't say anything about what b or c could be. So the cheekiest possible answer you could give to this question would just be to say, well, what if b is 0, and c is also 0, and a is just 1? Well, if you do that, then you just get q of x equals x squared. X squared is a quadratic polynomial. Its a value is non-zero, and its b and c value are real numbers. So I'm all good. And if x squared is equal to 0, then, well, this is the simplest one to solve. You take a number, you square it, you get 0. That number should have been 0. Okay, so that's all I'm going to talk about today. If you have any questions on this, then just send me an email or bring your questions to class on Tuesday for the review. And yeah, happy studying.